Xin chào anh Khoa, cảm ơn anh rất nhiều đã nhận lời mời tham dự của IBSG Podcast với chủ đề giải Nobel vật lý năm 2017. Trước khi bắt đầu buổi trò chuyện thì anh có thể giới thiệu một chút về bản thân mình được không ạ?
Dạ, wow. Anh hiện đang đi làm ở bên Mỹ. Hiện
Wow.
tại anh đang làm kỹ sư quang học ở Google. Thật ra cái LIGO này cũng có history đối với anh, tại vì hồi xưa lúc mà anh học thạc sĩ anh có làm một trong những cái luận văn của anh là về cái LIGO này.
Vâng, em cảm ơn anh. Bản thân em thì không có nhiều kiến thức về vật lý lắm, nhưng lại luôn cảm thấy rất là tò mò về những cái thông tin khoa học nổi bật trong lĩnh vực này. Cụ thể là em vẫn còn nhớ là năm 2016 trên TV có đưa một cái tin là về buổi họp báo ở Washington DC. Trong đó thì các nhà khoa học tuyên bố là họ đã thu được tín hiệu của Gravitational Wave và họ nói là chúng ta đã làm được. Sau đó thì các nhà khoa học quay sang ôm nhau với cả nở một nụ cười rất là hạnh phúc. Thì cái hình ảnh đó gây cho em một sự tò mò rất lớn là Gravitational Wave nghĩa là gì? Anh có thể giải thích một cách dễ hiểu cho em và các bạn hiểu về cái khái niệm này được không ạ?
Thì nếu mà nói về gravitational wave không á, thì nó rất là trừu tượng, rất là khó hiểu. Cho nên anh mới làm một cái slide deck, một cái presentation giống như ngày hôm nay, để anh có thể đi qua từ đầu, như là từ những cái căn bản cho tới cái việc thiết kế của cái hệ thống LIGO, cho tới cái việc detection. Okay, so LIGO. First, I'm going to say what is a gravitational wave. Second, the theory of relativity general. And then, of course, what is black hole? And then finally, what's LIGO? LIGO is very complicated. I want to say something about the concept of light interference. Tiếng Việt gọi là giao thoa ánh sáng. Uh, the second one is, okay, how gravitational waves is detected. Um, so LIGO is actually is very, very sensitive detector. And lastly, I want to go over, state of the art light science behind the LIGO. It sounds simple, but it's not really simple. I hope everyone here will appreciate that. Okay, so wave, right? So what is wave? The easiest one that we, just like you and me are talking right now, is sound wave, right? So wave is actually propagation of energy in the medium. The next form of wave is electromagnetic, right? The cell phone signal is electromagnetic. Light, as we see everything in the world, is also electromagnetic. Physics 101, this is back to the high school day. So electromagnetic wave consists actually, two types, right? The electric field and the magnetic field, right? So just leave it at that. Also, electromagnetic field is also propagation of energy. So how do these related to gravitational wave? We see electromagnetic wave and sound wave, all kind of wave every night, every day, just like sounds like we're talking right now. And if you go out to the pond, you drop a stone on the pond, it's create a ripple, right, on the pond. So this is exactly what a gravitational wave might look like. It's very hard to visualize gravitational wave because it is 4 dimension. The fourth dimension that Einstein added into his specific theory of relativity is time. So space and time are one. So that's why they call it 4 dimension space-time. It's easier to imagine, easier to visualize. Gravitational wave is like a ripple when you drop the stone on the water. The stone in this case is black hole, okay, or something really, really massive. So gravitational wave means space around us, like around you and me right now, being compressed back and forth. Right? Of course, we cannot feel this because it's too small. But if we do, then okay, we are going to die. That's not a good sign. So we cannot feel it because it's really, really small. How small is it? I would talk about that later. And this wave is actually predicted by Einstein in his general relativity theory in way back in the early hundreds, 1900s, which is more than 100 years ago. And so this animation right here is a very good illustration of how space is compress and expand because of gravity. Okay, so simply speaking, gravity is caused by the curvature or warping of space due to mass. Einstein correlate gravity to space and time. So that's really revolutionary here. So that brings up the concept of black hole. So black hole has never been observed. We never seen it because technically it's black. The reason is because the gravity is too strong. The gravitational effect is too strong that photon or electromagnetic radiation cannot escape. Therefore, we cannot see anything. There's no light escaping the black hole. Therefore, we call it black hole, right? So typically, black hole is formed when a dying star is coming to the end of its life. So the sun, our sun in the future will become a black hole, probably. So this is very important because this principle allows the scientists to construct and detect gravitational wave by LIGO. All right. So how we're going to detect space around us is contracting or expanding. The easiest way to do this is to use light interferometry, or gia thoa ánh sáng, right? Interferometry works on the principle of constructive interference and destructive interference, right? When light travel together, they add up constructively, create a bright spot, or they subtract each other and create a dark spot. The interferometer actually cut chia ánh sáng làm hai, right? Khi mà ánh sáng từ laser tới cái gương này, nó cut ra làm hai, một phần đi lên mirror 1 and then come back, and then một phần đi qua mirror 2 and then come back. At this point, tại điểm này tại cái điểm này hai cái sóng nó sẽ cộng lại với nhau. Tại sao nó lại có điểm sáng điểm tối? Tại vì cái quãng đường ánh sáng nó travel từ mirror 2 cho tới điểm này, and then từ mirror 1 cho tới điểm này nó khác nhau. Cái quãng đường từ mirror 1 and quãng đường từ mirror 2 là một the odd integer, right? Số lẻ của một cái bước sóng thì there's no interference. Không có giao thoa ánh sáng, một là sáng hay là tối, otherwise nothing, right? Nhưng mà nếu mà for some reason cái mirror either mirror 1 or mirror 2 or both of them chạy xa ra hoặc là chạy gần lại, interference will happen. Khi mà cái điều đó xảy ra, will cause black and white, right? So this is how LIGO is built. If we keep the length fixed so that the detector only see the bright spot or the black spot, right, and we just monitor it, right? But if the gravitational wave moves through the setup and displays, right, or move one of these mirror, and then we see a different signal, that's when we know, oh, aha, gravitational wave is here. So this is essentially how gravitational waves are detected. So this is the generic schematic. This is the real LIGO. The laser is here, right? The laser is gray in this building, split in half. One arm is this length, the other arm is this length. As they travel, they combine and analyze here, right? So each arm is 4 kilometers. Why not 2 kilometers? Why not 1 kilometer? And why not like 10 kilometers? So turn out the Earth is curved, right? 4 kilometers is actually the optimum distance before the curvature of the Earth come into effect, right? Why so long? Turn out we need this long to increase the sensitivity. Mới detect it. I will talk about that later, okay? But okay, now the question. So why so difficult to detect? Why it's too hard? Because of course because it's too small. And you might ask, okay, how small it is? So I put something into scale here. So the human hair is 100 micron. Inside your phone and your laptop, my laptop, the Intel GPU transistor is amazingly small, 22 nanometers. Okay, remember the wavelength is 400 nanometers. This is like 10 times smaller, which is already amazing, and that's like 10 to the 9. All right. If you go down further to the dimension of the hydrogen atoms, this is 10 yeah, that's like 10 to the 12. That's like 1,000 times smaller than the Intel transistor, right? But still not enough. If you go down further, you reach the quantum dimension of the proton, neutron, so on and so forth. And this guy is amazingly small at 1 femtosecond. That's like 10 to the negative 15 meter. That's just beyond imagination, right? So how small is gravitational wave signal? So for an arm length of around 4 kilometers, the detector must be able to detect a mirror displacement within the order of 10 to the negative 18 meter. This is 1,000 times smaller than the proton. I did some quick calculation. Detecting the gravitational wave is like you and I standing next to a Boeing 777 jet engine. You whisper and I try to listen to you. This is just how small it is. Okay, it's amazingly small. So how people can detect this? So turn out it's possible we can do this. We have to use like latest technology and knowledge in many fields, including laser physics, optical physics, mathematics, mechanical engineering, electrical engineering, chemical engineering, and the whole team has to be very careful and it's ultra methodical because it's just too much, right? What you need to do. This is actually one of the actual arms, right? The laser travel inside out this way and then come back. So why so difficult? The problem is when you build a microresonance interferometer in the lab, the first thing you might see is actually your own breathing, right? When you breathe, the air flow, right? And air interact with light, and it add noise to the signal, right? Or your heart is beating, it transmits to your bone, to the ground, and then to the optical table, and then to the laser, right? If you jump on the floor, the signal will be noisy as well. So the first thing they have to do is they have to suck the air out of this 4 kilometer tube. So inside here is vacuum. There's no air in this, and the pressure in the tube is so small. It's 1 billion times less than the pressure out here, where we normally breathing. So virtually there's no air here. So that's the first step, right? Remove all air, remove one noise, right? The second step, this is a little bit crazy. The next thing, so after the air, the next thing is vibration. So this is actually where I got involved. So typically in the lab, the optical table is floating, right? Floating means it's rest on air, right? Right. So air is really good dampen, right? So when you jump on the floor, the table is isolated. But that turn out is not even good enough. That's not good enough. Because LIGO is so sensitive, right? It's so sensitive that it can detect seismic wave. It's so sensitive that even it's I think it's a few hundred miles inland, but it can still detect ocean wave, right? And it also can detect earthquake around the world. It's so sensitive that it can detect earthquake in Japan, for example. So the scientists and the engineer have to isolate everything. Okay, so they have to design something that cut all the noise, cut all the vibration out. Okay, so LIGO, I cannot go into too much detail here because it's very complicated. So LIGO use a very elaborate suspension scheme, giống như là cái con lắc vậy đó. Right. So this is the mirror. This is the mirror. This is where the laser will interact with the mirror. The mirror is hang onto a double pendulum. Cái này là con lắc đôi á. This is just a mass, but the mass of this and the mirror is the same, right? And the whole thing here is hang into the wall on the ceiling. So this pendulum, the purpose is when vibration is coupled into the system, it has to travel to this first, to this, before it reach the test mass. And the job, the purpose of the metal masses and the The pendulum mass here is to cut or remove all those vibrations. So eventually this mirror will see zero vibration. You see this string? This is like 400 micron glass fiber. So it's not steel, it's glass. One of my project a while back is about this mirror. So this mirror is not a typical mirror. I'll talk about that later. So I have this. This is one of the tests.
Oh.
This is the actual mirror, and this is how the laser interacts. Vibration from the ground, right? We transmit to this frame, and then transmit to this fiber. But then the fiber and this fake mirror blocks everything.
Oh.
Okay, and therefore this actual mirror right here will see no vibration. The reason why we use fiber, because glass is a very good dampen. It's very good at blocking vibration. So it's essentially used to block every kind of vibration out of this mirror. All right. The next thing, okay, mechanical noise is solved. The next thing is the different one. The next thing is thermal noise and quantum noise. These are very difficult to deal with, right? Thermal noise is always there. Okay. Thermal noise, tại sao là thermal? Thermal ở đây không phải là nhiệt. Thermal ở đây là giống như là random motion của những cái molecule. Right? Giống như mình đang ngồi ở đây nhưng mà all the molecules still moving, right? Even in vacuum, even ở trong chân không, cái molecule vẫn còn moving. There is always some noise. There is always some motion of the molecules, right? Molecule never stay still unless you cool everything to absolute zero, right? Which is almost impossible and it's very costly, right? So thermal noise, especially in the mirror. Why? Because the laser is very powerful. The laser is like 25 watt, and then amplified to 800 watt. It's heat, right? So when you have heat, you add a lot of thermal noise. The next thing is quantum noise. So the quantum noise, why quantum? Because we're trying to detect something that's less than a proton. At that scale, when you go down to the atom scale, you have to be worried about quantum effect. The core of this successful wave detection is because of this very complicated and brilliantly engineered noise system. We need a lot of electro-optics, electronics, and signal processing. This is the actual arm. This is 4 kilometers. The whole thing right here inside that building. The laser itself, the laser is also very noisy, right? So the laser is 1 micron wavelength. This is infrared, hồng ngoại, and at 25 watt. This is very powerful. This can burn through steel. But the laser is not really at 1064 all the time, right? It will be 1064.1, it will be 1064 by 5, it can be 1065, and that's not good because when the wavelength change, the signal change, and therefore that is the noise. We have to stabilize the laser. Therefore, they have this, electro-optic modulator. These 3 mirror. This is a cavity. This is what we call the cavity. Cavity means it's like a trap, right? You send light in, it circulate back and forth in this cavity before it will keep traveling in this cavity until some condition is reached, and then it's accessed out of this cavity. So the purpose of this, the purpose of this is to make sure that we have a very stable power and very stable wavelength. This is the first stage. The second stage is the mirror. So this is actually this is one of my graduate project. I was involved with the design of the coating. So typical mirror, let's say the mirror in your rooms, right, is either silver or aluminum, right? These mirrors are different. Why we cannot use typical mirror? Because first, the laser is super strong. When it hit the mirror, it's 100 kilowatt. Aluminum cannot withstand this power. Okay, so when you if we use aluminum mirror, this laser will burn right through it. And interestingly, if you look at this mirror, it's essentially transparent. Notice how transparent this mirror is. You can see right through it. Yeah, because this mirror is specially designed for infrared. It's not designed for visible wavelength, but infrared will be reflected off. This is one of the test red laser that we try. This is one of the red near infrared laser that we use to verify that the laser is properly made. Okay, so the mirror coating, the mirror essentially is just a flat piece of substrate. All right, it can be glass, it can be metal or anything, and then on top of that you have to put some kind of coating, right? You have to coat it up. You can coat aluminum, just like what mirror you have in your room right now, or you can coat with something like a little bit more complicated. The coating of this mirror are, I believe, 25 layers. Each layer is around a few microns thick, and the material is, I cannot tell you, I don't remember. But one interesting I want to point out is, turn out there is an optimum way to select how thick each layer of the coating is, minimize the noise and maximize the reflectance. So that was done by genetic algorithm. Well, the next time, if you're interested, if everyone else is interested, I can talk about this. This project alone took me 3 months, and the entire department of LIGO several, I would say almost a year to come up with the final design. Yeah, again, the purpose of this coating is it has to be very efficient, right? Let's say 100% power coming in, we want 99% coming back reflected. We want that, but we don't want any noise. We don't want any thermal noise, right? Because the laser is too hot, it will heat up the mirror and therefore add a lot of noise. We don't want any of that. So therefore, the coating is very, very custom. This is something that we cannot find out there on the market. Okay. And what else? Interesting thing I want to point out is, let's see here. You see this dot? This little mirror right here, or this little piece right here, is to mimic the actual diameter of the laser beam. So the laser beam in reality will be this big. One interesting thing is, because the laser beam is this big and the laser power is 100 kilowatt, this portion right here will get hot, but the outside will not. Right? So what happened when you have one side is hot and one side is cool? We have conduction, right? When you have conduction, molecule will go back and forth in the mirror, and that is not good because that will add quantum noise and thermal noise, right? So one solution is, you see this? This piece is not only to hold the mirror, but this is also a heater. Yeah, it will heat the mirror. The reason is we do this to provide thermal equilibrium, to make sure that there's no molecule moving back and forth within the mirror. This is one of the design, these thing is very tiny, but it's turned out to be super important, right? So that's one thing I'd like to share. So the mirror itself is a science. And then, so after the mirror is done, the light go back here, go through this detection scheme. This is where light is converted to electric signal, electron. This is where photon is converted to electron. Your camera phone is a device identical to the device used in LIGO. So it converts light into electron, right? So that process is not efficient. There always is some noise. There is always some heat there, right? And that add noise. Again, that add noise. So the scientist or engineer has to engineer something else to, filter out all those noise, right?
Okay.
So one way, this I don't really know what does this do. I think this cavity is identical to this. Essentially, this is to clean out the laser beam, right? Make sure it's clean in term of the profile, right? In term of the light intensity. Make sure that it's uniform, so on and so forth. And then when it reach the photo detector here, there's a reason why they have to use two. I think they use two because at the end, after analysis and digital signal processing, they will subtract each of those. They will subtract these two from each other, right? And hopefully to cancel out the noise, right? Right. So let's say you have a signal, you add a noise, and then you have another copy of your signal with the same copy of the noise, right? When you subtract them from each other, you also subtract out the noise, right? And all you have left is your signal, which is very tiny, right? That's the main principle behind this. So the bottom line is a lot of these engineering in behind LIGO is to focus on denoising. That's all. The physics is very simple. The physics is light interference, but the engineering and all the physics to get there is, yes, it is amazing. That's why it won the Nobel Prize, right? So what does it see? This axis is time, right? The vertical axis is strain. So what does it mean by strain? Strain is essentially a fancy term to display the mirror displacement. So how far the mirror has moved, right? So from 0 to, let's say, half a second, or maybe 1/3 of the seconds, the mirror doesn't move anything, right? It just stays still. Look at the scale here. 10 to the negative 21. That's like 10,000 times smaller than the proton. But then from 0.355 to 0.455, and then suddenly the mirror moves. And that's why you see this chirp signal. This is the term for cái này gọi là chirp, nghĩa là nó move chậm từ đầu nên move nhanh lên. Right? Nó gọi là chirp. This graph mean right here there's no light because there's no interference. But from here to the end, there is interference. This interference indicate that gravitational wave has been detected. So, however, in reality, the scientists have to do a lot of check. They have to spend days and months to do statistical analysis, error analysis, to make sure that this is the real gravitational wave signal. This is the ultimate goal. And yeah, just one thing to pay attention to this map is this axis. You see, just look at the scale. You need 4 kilometers to detect, less than a femtometers, which is, I don't know, that's impossible. That's pretty much the talk here. That's basically the fundamental of LIGO. Before I end, so this LIGO is on Earth, and there is plan to send this into space. So essentially, they launched this entire facility into space. One of the, it sounds crazy, right? But why space? Because space is what? The temperature of space is 4 Kelvin. That's like negative 20 something Celsius, right? It's super cold, and then there's no air in space. You already cut down a lot of noise, and you can take advantage of the coldness of air to cut down the quantum noise, right? And also in space, everything is super quiet. You completely shield from Earth environment, right? No air flow, no seismic, no nothing. And so the plan is the scientists was hoping for the space LIGO will give even more sensitive detection of gravitational wave. So that's pretty much the discussion for today. I hope it's
Dạ vâng.
helpful and everyone enjoying it.
Em muốn hỏi là tức là cái phát hiện với các cái hệ thống LIGO system này thì đã mang tới cho các nhà khoa học giải Nobel rất là nhanh. Thì
Mhm.
em muốn hỏi là cái ý nghĩa của cái việc phát hiện ra cái gravitational wave này là như thế nào?
Ok. Anh thì không phải là anh không có học astrophysics, anh không có học vật lý thiên văn, anh cũng không có rành mấy, nhưng mà cái điều quan trọng nhất là cái thí nghiệm này nó chứng tỏ là Einstein đã chính xác cái này cả trăm năm rồi đấy. Cả trăm năm trước khi ông Einstein ông đã biết được ok sẽ có cái wave này theo như cái lý thuyết của em. Đấy. thì thì chứng tỏ cái thí nghiệm này chứng tỏ là cái vật lý, cái cái foundation của cái nền vật lý của nhân loại vẫn còn chính xác. Thì đó là về về và về ý nghĩa vật lý cho nhân loại. Còn về mặt khoa học kỹ thuật thì rất là nhiều khoa học kỹ thuật ở đây có thể được áp dụng cho đời sống. Mình không thể thấy nó bây giờ, nhưng mà biết đâu 10 năm có những cái technique dùng trong cái dự án này có thể mang ra ngoài được. Giống như cái hệ thống định vị vệ tinh toàn cầu hồi xưa là để cho tên lửa. Đấy, nhưng mà bây giờ everyone has it, right? Trong phone này cũng có GPS, something like that, right? And về mặt thiên văn thì I don't know. Thì về mặt thiên văn thì thường thường thiên văn có thể dùng ánh sáng, right? Lấy viễn vọng kính nhìn ra. Một cách nữa là dùng radio, right? Là dùng sóng radio. Một cách and then what else? Cái này là cách thứ ba, dùng gravitational wave.
Từ cá nhân anh là một người học vật lý thì anh cảm thấy như thế nào về cái phát hiện này của các nhà khoa học?
It's very amazing. Very amazing là con người mình có thể làm những cái mà gần như không tưởng.
Em xin cảm ơn anh rất nhiều đã dành thời gian giải đáp những câu hỏi của em, và một lần nữa em xin chúc anh gặt hái được nhiều thành công trong công việc và sự nghiệp của mình trong tương lai. Thì cảm ơn anh rất là nhiều.